So before we go any further, a real important part of networking, both wired and wireless, are the reality that we have to deal with collision domains. And what a collision domain is when two devices try to communicate over the same medium at the same time. We've experienced this multiple times in our lives, and we try to talk to somebody and we both start talking at the same time. We're on a phone and we both start talking, and there's that sort of awkward where people, like, one person will be quiet for a minute and you think like, okay, they're not going to talk, and then you start talking and they talk and everybody laughs. That's very much what CSMA CD does, or carrier sense multiple access collision detection. That's exactly what we do when we're talking to somebody on a phone. If we speak over each other, everybody sort of goes to that sort of awkward silence for a few seconds and then tries to talk again. So a switch device, when it wants to communicate, it's always listening on the interface. And we can see in this diagram on the right to help us illustrate what it's happening. So on the top left, we can see that the Ethernet device is listening on the interface. If it detects activity, it waits. It knows it can't communicate, because if it sends data over the wire, which is amplitude, energy, it's going to corrupt the data that's already being transmitted if it's already receiving information. If it detects a collision when transmitting, it then has to handle that situation. And what it's going to do is it's going to stop transmission and wait an arbitrary amount of time where it goes back into that listening state and starts over again. While transmitting, if it did not detect a collision, meaning no other device was trying to communicate when it was transmitting data, it can then keep communicating until the transmission's complete. So through this process, we can ensure that we can send reliable data while reducing collisions. But collisions still happen in switches today. You are losing packets all the time. The benefit is computers and network communications are so fast, we don't realize it anymore. 10 years ago, 15, 20 years ago, collisions on a network would slow things down dramatically. It would degrade the overall performance of a network, and it was noticeable to everybody using that network. But the benefit is we've gained so much speed in our networking technology that we're not even aware of these bad packets anymore, most of the time at least. So let's talk about an access point. An access point is a device that provides wireless connectivity to a network. And if you sort of take a lot of the devices we just covered, that's pretty much what you have at home in one singular device, and that's referred to as a SOHO device, small office, home office. Your SOHO router, it has a router functionality, it has a switch, and it has an access point all in that one device. In an enterprise, those would be separate devices to provide redundancy, availability, and fault tolerance. We're not going to get away with having a one-size-fits-all in a large enterprise. There's too much data, there's too much risk of data loss, and a failure of one device bringing down the whole network. So they separate these components out to different devices so that they can be redundantly managed. Access points operate in three distinct modes. We have access point mode, which most of us are familiar with. Essentially, the access point acts as an access for clients to access the network. It's the most common form. When we access somebody's Wi-Fi network, they give us the password, we're accessing in an access point mode. In repeater mode, the access point can act as a range extender, allowing us to retransmit communications between an access point and another recipient, or even another access point that's in repeater mode. And then last but not least, we have ad hoc, where you can have two access points directly communicate to one another. You could have two laptops that have wireless network cards in them talk directly to one another without requiring that central command authority or central access point to provide network access. They can peer directly to each other and not go through that central authority. So in this course, we don't cover wireless to really any degree other than what I'm going to cover here, but I wanted to provide some oversight on generally what is 802.11, the Wi-Fi standard, and some key characteristics of it, just so you have that knowledge, and particularly why most of our networks are really slow. And once we get there, you're going to sort of realize that a lot of the time it's not your internet, it's just the fact in how these devices were designed to begin with. So 802.11 in implementation is very similar to an Ethernet frame, but it's not an Ethernet frame. We still adhere to using a MAC address. We still have source and destination. We still talk about the payload size of how much data we're sending. But the key difference between an 802.11 frame and an Ethernet frame is that we have to have these three frame subtypes to better manage the network. Because in a switched Ethernet network, there's only one medium. You only have to deal with your device's communication and the switch. Whereas in a wireless construct, You have to deal with every other device. A microwave being turned on can cause interference. So there has to be a lot more work done in the communication side of a wireless network to provide a certain level of performance. So to do that, the 802.11 spec uses 3 frame subtypes, and that's a management frame, a control frame, and a data frame. Management frames, just like they sound like, handle the beacons, the authentication, the encryption, deauthentication. So when you initially connect to a wireless network, you're doing 802.11 management frames to authenticate and maintain access to that network. From there, control frames are used to control the signaling of the radio, because what's unique about wireless is that our radio has to compete with the RF spectrum of the devices around it, so we have to have special control frames that are constantly worrying about signal quality, interference, and they're telling devices what signals to change, what channels to change to, when it's clear to send, when it's not safe to send, so that we're not jamming each other and essentially colliding, having that collision occur on the wireless spectrum. And last but not least, we have our traditional data frames. This is where the data that users are actually sending over wireless networks are observed. Thing to note, data frames are the only frames in the 802.11 specification that are encrypted. Management and control frames are sent in clear text to anybody that's within range to pick up these signals and to observe these 2 packet types. And as we'd expect, 802.11 just can't keep up with the performance of an 802.3 Ethernet network because it takes considerably more packets between management, control, and data frames just to get one data frame over a wireless network than it would an Ethernet frame. So just like Ethernet, wireless uses carrier sense multiple access, but it uses collision avoidance instead of collision detection. And the reason it can use collision avoidance is because the specification, and particularly the use of control frames, provides a method to avoid collisions at all cost. So the 802.11 spec uses the acknowledgement subtype frame, a request to send, and a clear to send. So the acknowledgement is used to acknowledge every time a piece of data is received. Whenever a device would like to transmit over the wireless network, it sends a request to send packet. If the receiving access point hears that request to send and there is no current transmission, it will respond with a clear to send. But here's a problem with wireless networks. If your wireless network is being jammed by a microwave, another wireless network being nearby, your device will send an RTS packet, but if the access point never hears it, it will never send you a clear to send. Thus, your device will sit there and wait for some random amount of time and then try to do another RTS. So you can see right off the bat that these unencrypted control frames can be manipulated with because they're unencrypted and they're sent over a signaling medium that doesn't stop at the boundary of your house. Your neighbor can see these control frames and management frames, and it is possible to spoof CTS, RTS, and ACK packets and manipulate somebody else's wireless network. Another problem with CTF frames is that if you live in an area where there's a lot of access points around you, the problem is there's not enough unique channels for wireless communications over the 802.11 specification. So we have multiple access points using the same signaling, the same channels, and they're all sending CTS packets. So your device will see another network do a CTS and it will wait, even though it's not your network. It's a completely different MAC address. It's a completely different, everything. It's a completely different network. But the problem is you're both using the same signaling. You're both using the same frequency. You're both using the same channel. So even though a device on your network is ready to send traffic, if it keeps seeing these CTSs from another access point, it knows it can't communicate because as soon as it does, another device using the same frequency and channel is simply going to corrupt that packet and they're going to have to resend it again. So this is the death knell to wireless networks. The more networks you have in proximity to each other that are using the same channels increases the amount of RTS and CTS packets being transmitted. And everybody, regardless of what network they're associated to, adheres to RTS and CTS packets. So as soon as a neighbor moves in and turns their Wi-Fi on, they've slowed down your network. Because now everybody has to make sure nobody's talking, everybody's ready to send, and everybody does it in a very methodical approach, whereas if it was just your wireless network, you can make those decisions a whole lot faster. Let's talk about VPNs. While not a physical device like a lot of the other technology we've talked about, this is strictly a virtual approach to network communications. And VPNs are a reality today because of network speed, the use of strong encryption, and protocol encapsulation. And what that really boils down to is we're able to tunnel our private network communications using non-traditional protocols such as IP. We're able to send Ethernet frames over an IP packet across the network or across the world to another network. And this allows us to extend the range of our networks virtually so that both sender and receiver appear virtually on the same network, even though they've had to connect over the public internet to do it. So looking at this diagram at the bottom, we see that this is an example of a site-to-site VPN. Site A establishes a session with site B using an IP packet, the very common IP packet that every device pretty much uses on the internet. We then have an encrypted payload that within the encrypted payload, we send our Ethernet frames from our device. So we're able to essentially shunt our private communications to a completely different site. And this is how you can work for an employer that might have multiple distributed offices, and the mail server might be in Boston, and you're where I'm at here in San Antonio. And when I connect to the network and I use my VPN, it looks like that mail server could be in the next room. We're on the same network. From a logical perspective, we have the same IP addressing. The computer is almost blinded to the distance it had to travel to get to that device. And this really came about because the speed of the internet. Before VPNs, companies had to contact a telecommunications provider, say AT&T, and say, hey, AT&T, I need to connect my San Francisco office with New York. And AT&T would create unique leased circuits from that building all the way to New York, meaning they would go to every one of their communications centers and create a unique dedicated circuit. And as you'd imagine, this is extremely expensive and it took a long time to set up. And while they provided that pure end-to-end, point-to-point communications, they didn't have encryption. So anybody listening on the line could still collect your data. So VPNs really solved all of these problems. When network communications got faster, we realized, hey, instead of creating a dedicated connection, let's just shove our private data inside of an encrypted packet and just send it over to the traditional internet. And it's, just as fast as a dedicated circuit, but with now we can dynamically make VPNs to any device we want to connect to, so we don't have to wait weeks or months to get these circuits set up. It's way cheaper and it's just as fast. So the other type of common VPN connection that exists out there, and one that more people are familiar with, is the remote access connection. And this is what we would use. We would use a remote access type connection to connect to a VPN gateway. So our mobile device or our computer, we'd connect to that VPN provider to bypass our local ISP. So when we're doing our completely legal and legitimate peer-to-peer downloading, we don't want our ISP giving us issues about that. So we fire up our VPN to bypass all of our local ISP. But what we're doing here is when we connect to that VPN gateway, the VPN gateway is just in turn routing all of our requests out to the internet. We're not terminating and stopping at that, hosted provider. We're just being forwarded out to the internet. So doing this, we gain an anonymity over our internet browsing. We get security over untrusted network. We're at Starbucks. You don't want to connect to that untrusted network. So you fire up the VPN on your mobile device, and it now is sending all of your data through an encrypted secure channel out of that untrusted network. A VPN can be configured in two distinct ways, where we have this flow of communication where we send data to the VPN, it just redirects it out to the internet. And you could also have split tunneling, which segregates our private communications from our public communications. So split tunneling allows us to do what we're doing here, send data from our device out to the internet, or we can configure it so that our private communications and public communications are both sent to the VPN gateway. The benefit being we're able to segregate our public and private communications from the VPN based on our needs. If I need to connect to a server in that hosted cloud, I can send just my private communications over the VPN gateway. Or I want anonymity while I'm surfing online, I can just forward my public internet-bound communications over the VPN gateway and keeping all of my private network data in my home private network. So there's two different ways we can configure this, and your use case dictates which one you configure and which one you use. So in summary, let's cover some key points that I want you to remember. Switches use a store and forward method. They switch. They create circuits between interfaces. They receive an Ethernet frame with a source MAC and a destination MAC on one interface. It stores that Ethernet frame in memory. It then creates a circuit to the recipient or destination interface, and then flushes that Ethernet packet out through that circuit to the recipient device. And it does this back and forth between the two devices communicating, and while adhering to that carrier sense multiple access collision detection. Switches also use that CAM table. This table is a cache that stores and remembers what MAC addresses are associated with interfaces. And while we're not going to get really into network attacks yet, it is worth knowing any network device that stores a cache that is unauthenticated is ripe for attack. Common network attacks are conducted due to the abuse of the CAM table. Think about what would happen if I start sending Ethernet frames to a switch where I'm spoofing my MAC address and I say, hey, I'm not this MAC address, I'm the MAC address of that other device over there. Well, the switch is dumb. It's just going to start sending us all the packets that would have been intended to our victim now to us. So we can do that to steal data. We can do that to spoof and manipulate the flow of communications. We can redirect traffic. We can make traffic go somewhere it wasn't intended to go. And we can manipulate these communications once we receive them. And we'll talk more about that in a later module. But again, remember, anytime you have a network device that has a cache, and that cache can be accessed through a protocol that any device on the network can talk to, that's ripe for abuse. Routers route. It should be easy to remember, it's right in the name, but we route IP packets across dissimilar networks, meaning we need a router to get from network A to network B. And remember when we talked about gateways, a gateway provides a logical connection between two networks, but the networks don't need to be dissimilar. They can actually be a part of the same network addressing schema, but they're just physically separated. So because there's no addressing changes needed, we don't need a router, because routers make decisions based on how to get data efficiently from one network to a different network. So even if we have the same network type over a physical distance, a gateway would allow these two networks to talk to each other without the need of a router. Again, routers use route tables and algorithms to determine the most efficient path for communications. It assesses links ongoing every time it receives and sends a packet to a new link. It assesses the performance of that link and stores that in its route table. Routers also have those wonderful ACLs, those access control lists that we can use to restrict the flow of communications based on port, source network, destination network, and some other key characteristics. And this really creates a strong boundary for our network. This is what stops any network traffic from the internet to just blindly come in the front door to our private network. And remember, carrier sense multiple access is the protocol and process to either avoid or detect collisions, and Ethernet will detect in the sense that once it detects it, it will stop and wait a random amount of time before it tries to talk again, whereas a wireless network avoids it by using those control frames: clear to send, request to transmit. When it requests to transmit and gets a clear to send, we all know that our network is going to wait silently for that host that did the RTS until it sends and finishes its transmission. The next device will send an RTS to try to communicate and so forth. The problem being when we have multiple networks and they're all sending request to send and clear to transmit messages. And again, VPNs provide that logical network extension. So instead of creating a dedicated circuit between our offices, we can use that site-to-site VPN. We're using the power and speed of the protocols and the internet infrastructure that exists today to just encapsulate and encrypt our packets and just send them over the internet. We're taking our private network comms and just tunneling it through the public internet. And the benefit is both software solutions, the VPNs on both sides, just dump that data back out as if it was local network traffic. So other devices around it are unaware that that came from a VPN. And that's what makes all of our local network traffic work over the public internet when we use VPNs.